Hi, welcome to recap of root survey, root locals, Bode and polar plots. This is part number 3. Okay, this okay. Last video we were discussing what is the importance of omega GC. Omega GC, as the name itself indicates, omega GC stands for it is the frequency at which the magnitude of GFS into HFS is equal to 1 or 0 dB. So it is uh, G of G of G omega and H of G omega is equal to 0 dB. It is that frequency which corresponds to this magnitude, which is 0 dB, is nothing but omega GC. Gain crossover frequency, where the gain crosses 0 dB line, or where the gain is 0 dB, is called as omega DC. It is the frequency we are talking about. At what frequency this is solved. Next is omega DC. So here it is phase crossover frequency. Omega is frequency. This is phase crossover. It is the frequency in radian per second, where phase of the GFS into HFS is minus 180 degrees. So you'll want to have the phase equation where the phase is equal to minus 180 degree. The corresponding frequency is omega. So why we are looking at this 0 dB of magnitude, which corresponds to 1 and minus 180 degree, is because we are looking for a system whether it is oscillatory or not. Suppose if you consider CFS by RFS, which is nothing but GFS by 1 plus GFS into HFS, you can see this is what we are considering. So this is GFS into HFS, which is nothing but the open function. We are looking at whether this is minus 1. The moment when this becomes minus 1, you can see this is GFS, it is 1 plus of minus 1. So when this GFS into HFS becomes 1, this becomes 0, and then the overall this will become infinity. So that system is, so without input, without actually RFS, system is started giving some output which is oscillatory output. So we are looking at GFS into HFS when it is minus 1. So we know that this minus 1 can be written as 1 at an angle minus 180 degree. See now, this is that 1, is that minus 180 what we are discussing. So this is that 1, this is that minus 180. So you are looking at what frequency the magnitude becomes 1, at what frequency the phase becomes minus 180 degree. So this corresponds to omega GC, this corresponds to omega BC. So these two are very important while deciding the stability of the system. Okay, next question is uh, what this is question number 19. What is gain margin? What is gain margin? So now how do you define gain margin of a system? So assume that so if you want to define gain margin of a system, it is the margin by which the existing gain, if it is multiplied, then then the system is oscillate. Oscillate. It is the margin by which the existing gain, if it is multiplied by this gain margin, the system will become oscillated. Assume that the existing gain is around 40. The gain margin is, assume that it is plus 15 dB. So what is plus 15 dB corresponds to? This corresponds to 10 to the power of 10 to the power of 15 by 20. This comes out to be 5.623. So now this is your system gain. This is your existing system gain. System gain. If the existing system gain is multiplied by 5.623, which is the gain margin in ratio in absolute value, then this will become into 40. What is this? It is 224.53. So now what? It is the margin. It is the margin by which the existing gain, if it is multiplied by this, then system is oscillatory. If the value of k of the system, if the system is 224.33, system is oscillatory. Same thing is true. Assume that we consider another system where the existing gain is around 50 and the gain margin is minus 6 dB. So what is this minus 6 dB? So this my 10 to the power of minus 6. Okay, let me just open this. Minus 6 by 20. It is 0.511. Sorry, 0.50. Meaning, if the existing gain, system gain 50, if it is multiplied by the gain margin, which is 5.011, which is now into 50, we become 25.059. So at this value of k, system is oscillating. So what did I say? If the it is the margin by which the existing gain of 50, if it is multiplied by the gain margin, then whatever, if this is your system gain now. If the system gain is this, then system is oscillating. System is, if it is multiplied by the gain margin, then system is oscillating. A system with 50 was unstable system, was giving minus m. So when k is equal to 25.05, system is oscillating. I will not say system is unstable now. I will simply say it has got a gain margin of minus 60. So to decide the stability of the system, I should know both gain margin as well as phase margin. Both should be known. So we will discuss that. If both are positive, system is stable. If this is positive, this is negative, then also it is stable. This is for a stable condition. When it is unstable, it is, when I say positive, positive in terms of dB, negative in terms of dB, positive degrees, phase margin, if it is plus dB and plus degrees, phase margin, system is stable. Gain margin is negative dB, but phase margin is positive degrees, system is still stable. When does the system is unstable? Gain margin is negative and phase margin is negative, system is unstable. When phase margin is negative, even if you have a positive gain margin, system is still unstable. When does the system is oscillatory? When gain margin is 0 dB and phase margin is 0 dB. 0 dB. This is about the gain margin, phase margin, and omega PC and omega